Good evening, everybody. I'm Rick Gering from Naperville Astronomical Association, and tonight we're going to spend a little time talking about asteroids, which is another one of my favorite things to find in the sky and share with others. And I'm amazed all the time at how often even very experienced observers have absolutely no idea how to observe asteroids, how to find them, where to look for them. But we're going to cover all that tonight, and we're going to find out that there really isn't all that much to it. So let's go ahead and see what we can find out. First question is, what is an asteroid? Well, at its most fundamental level, an asteroid is a chunk of rock and metal that orbits the sun. They're fairly small. The biggest is Ceres, which is now classified as a dwarf planet, but it's only 590 miles in diameter. The smallest are measured just in feet. Now, most asteroids live in the asteroid belt between Mars and Jupiter, and we'll talk a little later on about why that happened. And they're very small. All of them added together would make a ball smaller than our moon. There are different types. We'll talk about that very briefly, depending on what kind of rock and metal they're made up of. And functionally, they're the leftover building blocks of the solar system. If Marlon Brando were talking about them, he would probably say, and they could have been a planet. But to find out why that is, we're going to have to back up a little bit and talk about how the solar system came to be. So how did that happen? Well, it all started with a cloud of cold gas in space. Hydrogen molecules floating in the space between the stars, mixed in with some heavier elements that were made in earlier generations of stars and went back into the mix when those stars died. We can see places like this today in the Orion Nebula and other stellar nurseries that we find in various parts of the sky. About 4.5 billion years ago, it was in one of those hydrogen molecule clouds that the solar system first started to develop. And the first thing that happened was a relatively dense clump started to form. Some of those molecules of hydrogen were bumping into each other and sticking, partly as a result of random collisions, and probably in our case helped along by the forces that accompanied the explosion of a nearby supernova, maybe some stellar winds from a nearby star, or just the gravitational pull of a large star that was passing through our neighborhood. But for whatever reason, this dense core began to form, and as it became denser, its gravity became stronger, its mass increased, and it began to draw more material into itself. And as that clump grew, it started to spin because of the motion of the infalling material. So now we have a spinning, growing clump of stuff, constantly growing, gravity getting stronger and stronger, pulling in more and more material, and eventually that clump reached a critical point where it was no longer able to resist its own gravity, and the clump collapsed into itself in an instant, in what's called a gravitational collapse. As the clump collapsed inward, the material at its center condensed into a dense spinning protostar that later on turned out to be our sun. The remaining material in the clump continued to spin, just like the protostar did, but as it spun, it flattened itself out into a disk surrounding the protostar, with a donut-shaped envelope of material out beyond the edges of the disk. More and more of this matter was drawn into the protostar at the center of what used to be the clump, and what is now the nascent solar system. Its mass and gravity continue to increase, and by the time the process is done, over 99% of the total mass of the disk is going to end up in the star, with only 1% making up the whole rest of the solar system around it. Eventually, as that star continues to amass material, the pressure and the heat at its core keep going up and up and up and up until it becomes there's so much pressure and so much heat that the hydrogen molecules it was made up of can no longer maintain themselves as molecules. They're ripped into individual atoms. And beyond that, it continues until the atoms themselves can no longer maintain their integrity. Their structure collapses, their components reassemble to form atoms of helium, and in the process, huge amounts of energy are released. And now we have a nuclear furnace, and a new star begins to shine. And that was where we got our sun. Now, meanwhile, out in the disk, more clumps are beginning to form in the material that's still spinning around the very young sun. In the area close to the sun, rocky planets are taking shape through accretion as material bumps into other pieces of material. And as long as they don't hit each other at too high a speed, they tend to stick together. A series of these collisions builds up a sort of protoplanet called a planetesimal, and they start building up in various areas near the sun. Farther out, the same thing is happening to the material that will ultimately become the asteroids. And even beyond that, near the outer edges of the disk, temperatures are colder, and the disk and its planetesimals are composed, instead of rock, they're composed of mixtures of rock and ices. Then finally, the final step in creating the solar system was the planets clearing the path of their orbits. In the inner solar system, where the rocky planets formed, the planetesimals collide, growing larger and larger, ultimately forming the planets and clearing out the material in each planet's orbital lane, more or less. We're going to see later that none of them really cleared everything out. Out in the cold outer edges of the solar system, there's still quite a bit of the hydrogen molecular gas that the disk originally formed from, and planets forming out in that area draw that gas in, layered over the rock ice core, and create the gas giants, Jupiter, Saturn, Uranus, and Neptune. But at the boundary of those two zones, in the asteroid belt between Mars and Jupiter, nothing grows larger than the planetesimals. So what went wrong out there? Well, the answer to that question can answer that question in one word. What went wrong in the asteroid belt was Jupiter. Jupiter, the big bully of the solar system. As we said earlier, 99% of the mass of the solar system went into the sun. Of the 1% that was left, 2/3 of it went into Jupiter. So if you take all the other planets and their moons and the asteroids, everything else in the solar system, put it on one side of the scale and put Jupiter on the other, Jupiter is about twice as massive as everything else other than the sun put together. And why did that cause a problem? Well, during the time when the planetesimals were forming and bumping into each other and trying to stick together throughout the solar system, big old Jupiter was coming around quite close to the orbit of the asteroids. And when pieces would bump into each other and try to form larger pieces in that part of the solar system, Jupiter would come along and its gravity would be strong enough to tug them back apart as it went by. And that is why none of the why no planet formed in the asteroid belt, because of the effect of Jupiter. And if you're wondering why it was that Jupiter prevented formation of a planet in the asteroid belt but did not prevent the formation of Saturn out beyond it, the answer is that the asteroid belt is about half as far from Jupiter as Saturn is. So Jupiter's gravity was far less influential out where Saturn was. It was twice as far away from Jupiter as the asteroids were, and it was the asteroids that were disrupted while Saturn was not. So what's the difference between asteroids and planets? Well, the difference is mass. Under the current definition of what constitutes a planet, it's an object that orbits the sun directly. In other words, it's not going around something else, it's going around the sun, like our moon goes around the Earth, which is why the moon's not a planet, but the Earth is, because the Earth orbits the sun directly. The moon also orbits the sun, but it does it by orbiting Earth. Planet also has to have sufficient mass to achieve hydrostatic equilibrium, which sounds like something really technical, but guess what? It's really simple. All it means is it's round. And if you think about the way the planets formed, with bits being added as time went by, and you think about the fact that mass that's forming has a center of mass that is the source of its gravitational pull. If that gravity is pulling from all directions at the same strength, you're going to end up with a sphere. And if you have enough mass, that's what will happen. The definition refers to it as hydrostatic equilibrium, but all it really means is it's round. And then the third criterion to be a planet, and that's something else, is that the planet must have cleared smaller bodies from its orbit. And again, as I said before, we're going to see before we're done tonight that isn't really true of any of them, but we still make believe that it's part of the definition anyway. Dwarf planets, which are Pluto, the asteroid Ceres, and some of the objects out beyond Neptune that Mike Brown's team at Caltech kept finding, they would be planets except for the fact that they have not cleared smaller bodies from their orbits. And asteroids, which are smaller even than dwarf planets, they have not cleared smaller bodies from their orbits either, but they also don't have enough mass to make themselves round. So asteroids are not planets for both of those reasons. Let's see what they do look like. Up at the top left, we have Ceres, which is the only asteroid that's a minor planet because it has made itself round. And you can see, though, that other asteroids are far from it. Some of them don't even look like they're trying. Vesta comes pretty close. It's the second largest and an almost round asteroid, but we have asteroids like Eros down there at the lower left that looks like one of those Dutch shoes to me. Steins, which looks sort of like an arrowhead. Itokawa, that looks like a peanut that a squirrel ate half of. All sorts of shapes, but none of them are round, although some asteroids do have moons. We have Dactyl over here that's rotating around the asteroid Ida, but you will not be able to see any of the moons in your telescope because they are just way, way, way too small. So how small are they, you ask? Well, Earth is 7,900 miles across, and the largest asteroid, Ceres, is 590 miles across. That moon that we were looking at a minute ago, Dactyl, that swings around the asteroid Ida, is less than 1 mile in each axis. So it's very, very, very tiny. And most of the asteroids as you can see, are not very big. As we said earlier, all of them together would be smaller than our moon, which is a couple thousand miles across. So where do they live? Well, asteroids, most of them live in the asteroid belt. Some of them do not. Most of the non-belt asteroids are in Jupiter's orbit, and they're called Trojan asteroids. They are sort of parked at two of the stable points in Jupiter's orbit, the so-called Lagrange points. There's one that's 60 degrees behind Jupiter and one that's 60 degrees ahead of Jupiter, where objects can sit in Jupiter's orbit and not be tugged or disrupted by Jupiter's gravity. They're sort of safe spots in the orbit of Jupiter, and quite a large number of asteroids have congregated at those two spots. Some of them are named for Greek warriors from the Iliad, and others are named for Trojan warriors from the Iliad. Trojan asteroids have also been discovered in the orbits of Mars, Neptune, and even a few around Earth. So I'm not sure how we fit Jupiter, Mars, Earth, Neptune, or any of them into the current definition of a planet, but there you have it. There are a few other non-belt asteroids. Other ones outside the belt are primarily the Hildas, which are shown here in blue, inside the orbit of Jupiter. They go around the sun three times for every 2 trips Jupiter makes. And they're at Lagrange points with respect to Jupiter's orbit. They congregate at the 60-degree points ahead of and behind Jupiter, and also at the point directly across from Jupiter, which is also a stable point in Jupiter's orbit. Inside the Hildas, we have the main belt, which is shown in white. And those of you who are familiar with the details of Saturn's rings are going to notice immediately that the asteroid belt, like the rings, has dark gaps in there called Kirkwood gaps. And those, again, are areas that are in orbital resonance with Jupiter, except in this instance, while the orbital resonance with respect to the Hildas is keeping the Hildas in that space. In the case of the Kirkwood gaps, they're points at which Jupiter's gravity is forcing things to pretty much stay away, which is why we have those nice, fairly well-defined dark rings within the white belt of the asteroid belt. And then inside the asteroid belt, we have the so-called near-Earth objects, or NEOs, and they come into different classes depending on whether they cross Earth's orbit. And if they do cross Earth's orbit, are they asteroids that are usually farther from the sun than us or closer to the sun than us? Because when it comes to near-Earth objects, it's all about us. Now, there's one thing that all of these non-belt asteroids have in common, and that is that from this point on, I'm not going to say anything about them tonight, because what we're here to really talk about is how to observe asteroids with our telescopes. And you're not going to be able to easily observe any of the non-belt asteroids. So let's talk about the ones that we can get at, which are the belt asteroids. As I said earlier, I am constantly amazed at how many people who have been out using their telescopes for years and even decades, how many of them have never gone after asteroids, and they all have an excuse. I don't observe asteroids because they're too faint to see in my telescope. And if you tell them no, they're not too faint to see in your telescope, then they'll come back with, yeah, but I don't know if any are visible tonight. And if you tell them that there are ways to find that out, they'll say, yeah, but I don't know where to look for them. And if you show them how to look for them, then they come back with their ultimate argument, which is they just look like little stars anyway. And the fact is, are they just looking for an excuse? Well, let's look at those reasons and see how they stack up. So excuse number one, asteroids are too faint to see in my telescope. Well, you know, there's something to be said for that. Asteroids aren't stars. They only shine by reflecting sunlight, and some of them reflect sunlight better than others. If you look at the asteroids up at the top right corner, you can see even there's even sometimes within the same asteroid, there's areas that reflect better and areas that reflect worse. It largely depends on what the asteroid's made of. Most asteroids really don't reflect very well. They're called chondrites. They're very dark material. They have an albedo or reflectivity index of only about 3%, but they make up 75% of all asteroids. So most chondrites you're never going to be able to see in your telescope. That's true. But all asteroids are not chondrites. The silicates, or the stony asteroids, they're fairly bright. They have an albedo of 10 to 22%. And the metals, which are made of nickel and iron, they have an albedo of 10 to 18%. And just by way of comparison, the light areas, or the bright areas rather, on the moon have an albedo of 11 to 18%. So stonies and metals are both right about the same reflectivity as we see in the bright parts of the moon. Now, asteroids, of course, are not as bright as the moon. Excuse me. I mean, asteroids are not as bright as the moon because they're much farther away. And that's the other factor we have to take into account in determining how bright asteroids are going to be. It's going to depend on where they are in their orbits around the sun and where they are with respect to Earth in its orbit. And as you can see in the drawing here, the point where asteroids are closest to us is when they are at opposition, which means they're on a straight line from the sun to the Earth to the asteroid. Not only are they closer to us at that point than they are anywhere else in their orbit, but it's also a point where the sun is illuminating them directly, so the entire face of the asteroid is always being illuminated from our perspective when the asteroid's at opposition. Now, all oppositions are not created equal, although this diagram sort of is a little bit misleading because it kind of suggests that they would be. But Earth's orbit and the asteroid's orbit are both ellipses or ovals, not circles. So there are going to be times, depending on where the asteroid is in its orbit and where Earth is in its orbit, sometimes they're going to have closer oppositions and sometimes they're going to have oppositions that are farther away. And obviously when they're closer, they're going to be brighter. When they're farther away, they're not going to be quite as bright. And this is all happening in 3 dimensions. So sometimes the asteroid is above us or below us when it reaches opposition. And in those cases, it's going to be a little farther away than if it's even with us. But still, all that being said, the asteroid is going to be brightest when it's at opposition, and brighter still if it's a favorable opposition. So where does that leave us? What does all that come down to? Well, it comes down to this. There are at least 25 asteroids that are going to reach magnitude 9.0 or brighter at favorable oppositions. Now, that pair of binoculars that you bought years ago to take to football games with you is probably a 50 millimeter objective, about 2 inches across. And those binoculars can see down to about magnitude 10 or 11. So if you can see these asteroids in those binoculars, I guarantee you can see them in your telescope. And so that first excuse, they're too faint to see in my telescope, busted. Let's look at excuse number 2. I don't observe asteroids because I don't know if any are visible tonight. Well, there's a 3-word answer to that question. Can you read? Because if you can read, you can find out whether any asteroids are visible tonight from where you're sitting. You can get, excuse me, you can get that from books like the Observer's Handbook. You can get it from magazines like Astronomy and sometimes Sky and Telescope. And if you don't have the book and didn't buy the magazine this month, you can go online and get it from inthesky.org. And up until a month ago, you could also get it from another site called CalSky. So what do we find in these sources? Well, Astronomy magazine is surprisingly good when it comes to asteroids. Almost every month, in fact, maybe literally every month for as long as I can recall, Astronomy has always featured an asteroid that is relatively easy to find and bright enough that it's going to be pretty easily visible. Sky and Telescope, for reasons I do not understand, not so good on asteroids. They very, very infrequently feature them in the monthly edition. They're a little bit better with their online materials. Bob King, who wrote the article that's shown there in the center of this screen on Pallas and Iris, is one of their guys who frequently will tell you about asteroids that are easy to find and easy to look at. Over on the right, we have one of the asteroid pages from this year's Observer's Handbook, which is published by the Royal Astronomy Society, Royal Astronomical Society of Canada, and it will tell you, for example, asteroid 5 Astrea up there at the top left reached opposition this year on January 22nd at magnitude 8.9, and then it tells you some of the dates and magnitudes and locations where Astrea was before and shortly before and shortly after opposition, when it was a good thing to find. The handbook covers every asteroid that will reach magnitude or be brighter than magnitude 10 during the course of the year. So to make the cutoff for the handbook, it has to reach at least magnitude 9.9. As I said, if you don't have anything in print, you can go to inthesky.org and you tell it where you're at. You can see on the right-hand side there, the user-specified latitude and longitude that I put in. If you don't know your latitude and longitude, it's easy enough to find out. If you go to Google Maps and left-click on any point, Google will tell you the latitude and longitude of that particular spot on the planet. And if you put that into inthesky.org and ask it, hey, what's going on tonight, or for any other night that you specify, it'll give you a list of asteroids that can be seen from that location. It'll tell you which ones they are, what their magnitude is, so you know how bright they're going to be, what constellation they're in, and it'll even tell you what time at night you should be able to see it. If you then get a little more detailed with that same site, in this instance I picked asteroid 8 Flora to see where it would be this weekend coming up here. And, you can see down at the bottom, November 20th, where it's going to be, its right ascension and declination, which are its coordinates on the sky if you're using either sky mapping program or a set of sky charts. It tells you what time it will rise from above the horizon here, what time it culminates or crosses the southern meridian, and then what time it sets, and again, its approximate magnitude. So we then have similar information that was in CalSky, which, as I say, unfortunately stopped operating about a month ago. I'm still kind of keeping my fingers crossed that somebody might pick it up and reactivate it, but that becomes less and less likely as time goes on. So we won't spend any time talking about CalSky tonight. But in any event, the excuse that you don't know if any asteroids are visible tonight, busted. So how about excuse number 3? Okay, I can see them and I know they're going to be there, but I don't know where to find them. Well, again, if you go back to the same sources that we just talked about, the RASC handbook has coordinates which would require you to get out some sky charts and plot their locations, and I don't expect you to do that. But Astronomy magazine has charts that will show you where Ceres is going to be in relation to other stars in the sky during the whatever period. This was from the February 2009 Astronomy magazine, and was talking about where asteroid Ceres was going to be that month. Or if you go again to InTheSky.org and tell it where you are, it will generate a map of how the sky will look from your location. And unlike what you can do with Astronomy magazine's chart, you can zoom in and out of the chart that you'll get on InTheSky.org. So here, for example, we've got a very wide view of where Fortuna is going to be during the week of September 23 to 30 of this year. You can see that magenta line up there where it says Fortuna is its path during that period of time. You can tell both from the shape of the constellation and also from what it says at the bottom there that you're in the constellation Aquarius, and so that can get you oriented. And then you can zoom in and get a much more detailed look at where Fortuna is going to be. You can see the triangle of bright stars here, top left, bottom left, and center right is the same triangle that we saw over here when we were looking at Fortuna earlier. There, and up there. So you can move back and forth between the zoomed in and zoomed out views, and it's not too hard to find. Again, on the left-hand side, we have how that used to be done in CalSky. Since it's not operating, I won't go through that. And if all else fails, if you have a go-to telescope, even the most basic go-to that I can think of, which is the AutoStar 497 hand box, even that includes 26 asteroids. So if worst comes to worst, you don't have to do anything other than read your owner's manual and figure out how to tell the telescope that you'd like to go see an asteroid tonight, please. However, let me add one caveat to that. If you want to find asteroids using GoTo, that's fine. Those of you who have heard me speak before know that I'm not a fan of GoTo. And one of the reasons is this. You know and I know that if you have a GoTo scope, you know this, and I certainly know this. Where you tell the scope to take you and where it actually takes you is not necessarily going to be the same place. And it's certainly not, except in very rare instances, going to be precisely the place you ask it to take you. So in order to figure out which of the things you see in your eyepiece is the asteroid, you're going to need a chart. So bring one with you. Bring your astronomy magazine, or print out do a screen print from in the sky, whatever, so you can compare what you see in the eyepiece to what you see on the chart, and know for sure that what you're looking at is, in fact, the asteroid. The chart that you see here is one that I actually used in August while I was running down Ceres. If you look around August 16th, you can see there were stars magnitude 7.5, 7.6, 7.4, and 7.9 that were all pretty close to the August 16 location of Ceres. There were other stars nearby that, although they aren't marked, were about the same magnitude. So figuring out which was Ceres and which was one of those stars would have been quite a trick without having the chart. And here's the danger. There was a guy a few years ago who was at a gathering, and he sent an email around to everyone talking about how he had shown so many people Ceres in his telescope that night, and how everyone was very impressed with its pretty blue-gray color. Well, if you've never seen Ceres, that may not mean anything to you, but if you ever have, you know that that's kind of the same as sending an email around saying that you showed a lot of people the planet Mars and everybody was impressed with how green it looked, because Mars isn't green and Ceres isn't blue-gray. And I know that the guy who sent that email has a go-to telescope. And I don't know what his go-to telescope took him to that night, or what it was that he was looking at and showing people and passing off as Ceres, but I guarantee it was not Ceres that he was looking at. So don't let that be you. All you need to do is bring a chart with you and compare it to what's in the eyepiece. If your go-to telescope is looking right, or is working right rather, what you see in the eyepiece is going to look like exactly what you see on the chart. It's going to be very, very simple to confirm. And if your go-tos are not working, well, you probably ought to know that, and not just proceed as if they might be. So with that having been said, the excuse that I don't know where to find them is busted. And that finally leaves the ultimate excuse of people who don't observe asteroids. Why bother? Because they just look like little stars anyway. Well, that's something that's often said, or I think more accurately assumed, by people who have never seen an asteroid. And I will admit the difference is subtle. It's like the difference between a semi-gloss finish and a satin finish. But I also know this. I've shown asteroids to quite a few people, including quite a few surprisingly experienced amateur astronomers who had not seen asteroids before. And every time they have asked me, I got all this stuff in the field, which one's the asteroid? I have always answered the same way. I always say it's the one that looks different from all the others. And looking at the field in the eyepiece, everyone I've ever said that to has been able to identify it. No one has ever had to ask twice. So the excuse that they just look like little stars anyway, busted. And that pretty much covers all of the excuses for why people don't observe asteroids. So don't be this guy. Don't get home from spending all night out under the stars and get up the next morning and say, oh my God, I could have seen an asteroid. They're easy to find. They're interesting to observe. They're not difficult. It's a nice change from revisiting the same Messier objects over and over. They have a unique appearance that once you see, you'll always recognize. And frankly, it'll impress even experienced astronomers if you can put one in your eyepiece and let them see it. So before I finish, one more thing to do, and I have to do this so I don't get those emails that start, "Sir." This is for the purists. They would tell you, and okay, I admit they are probably correct, the only way to really be certain that you saw the asteroid is to find what you think is the asteroid, either sketch or photograph the field. I think even a purist would let you photograph it, although some might insist that you sketch it, showing at least 3 or 4 stars nearby for context. Or what I used to do when I cared about this was put a little pencil mark on the chart, on the star chart, to show where the asteroid was the first time I saw it. And then you have to come back later to confirm that the asteroid has moved in relation to the nearby stars. Because if you don't do that, it's possible, it's always possible, that what you were looking at was actually just a field star that happened to be about the same magnitude or brightness as the asteroid. Now, asteroids usually move about 30 to 40 arc seconds per hour at opposition. So you're going to have to plan to come back at least a few hours after your original observation. And sometimes, you may have to come back the next night in order to confirm it. Personally, I don't think that's necessary. The purists would send me those emails telling me how wrong I am. This slide hopefully will prevent them from doing that. But let me put it this way. You won't have to do that in order to convince me. So that's what I know about asteroids and how to find them and how to observe them. If anybody has any questions, comments, suggestions, accusations from the purists, let me know.
We do have one question from Steve, and he asks, do any rotate rapidly enough to see light variations while viewing? So are any in a tumble where you maybe get different reflectivity, if that's a word?
No, I don't think so. It's not impossible, but I mean there are very few things in all the sky. There's very few naturally made things. I mean, man-made stuff's another question. But other than the moon Iapetus, which has that dark side, light side thing going, it's the only thing I can think of that actually has a really distinctively different albedo on one side versus the other side. So let me put it this way: if there is an asteroid that does that, I'm not familiar with it.
Okay, that was the only question we had. And if anybody wants to try to get another one in real quick, otherwise I think we're done, Rick.
All right. Well, everybody have fun. Get out under the stars. It's starting to clear up again tonight, so if you got some time, go on out. There's a comet on Orion's shoulder tonight that you can maybe see in binoculars. It looks like it's going to about magnitude 9. I'm going to go out and see if I can pull it in. And
what time is Orion already up?
No, actually, I think it's going to be. I've got some trees to my southeast, so I'm going to plan to go out about 11 or 11:30, but it's going to be up before then. I do not think it has risen yet, though.
Okay.
So, all right. So good night, and thanks for listening.